Okay. Yep. So I actually gave the majority of this presentation at the Concrete Institute conference just under 2 years ago in Perth. And when I was looking at what to present to this group, I sort of went back to this as a starting point and sort of realized that for better or for worse, and probably consider unfortunately, things haven't changed a great deal. So I'll run through this. Hopefully it's of interest, and if there's any questions along the way, feel free to shout out, or we'll have some time at the end. So I'll just go back. The elephant sitting on the concrete pipe, it was brainchild of our marketing guys addressing the elephant in the room. And yeah, look, we developed this concrete some time ago and have called it Eco Pipe. So I'll be referring to Eco Pipe throughout. So in terms of the opportunity, I thought it was interesting to quantify exactly how much concrete goes into pipes, and it's not easy to do this, but back of the envelope sort of numbers. And again, this was a couple of years ago, probably haven't changed a great deal. I sort of worked out it was roughly 1% of the concrete in Australia goes into pipe production. So it's not a great deal at the end of the day, but still we love to compare to other metrics. So based on the EPD that we had done a couple of years ago, and this is excluding any installation related embodied carbon, but it's roughly 200,000 tonne of CO2 emitted in the production of concrete pipes. And got to compare it to something. So it's like driving a car around Australia 91,000 times. So RCPA set out some time ago to develop this, but before I get into the nuts and bolts, I'll just run through quickly the process around production of concrete pipe, because it is quite different to those that are familiar with sort of concrete that's poured into flat work or poured into precast forms. So it started out in a very laborious process. This is sort of the evolution, I guess, from hand-placed brick drainage conduits, where they were hand tamping a relatively stiff and dry concrete into molds. Around the start of the 20th century, there was a spinning process developed, referred to as the Hume spun process. This was evolved, another process developed called the roller suspension process, and those were widely used in Australia over the last decade to produce pipes. However, in the US in the 1950s, a process was developed to use basically mechanical compaction system. So either a series of rotating roller heads or a vibrating core that would allow you to make vertical products, so pipes in a vertical form. And it's just generally referred to as vertical casting. This is pretty much the dominant method of making concrete pipes around the world these days. And it's what RCPA uses. And it's one of the reasons that we were able to develop a low carbon concrete is because of this process. I've got a short video, which I would want to put in full screen, but it's not going to play. So first step is manufacturing the reinforcing cage. These are done on automated machines that produce a bespoke cage. This is the concrete being placed into the form with the rotating compaction head going into the barrel of the pipe. So you can see the nature of the concrete. It's very stiff, very dry. The pipe mold is shown there. The concrete's been compacted by that roller head into the mold. The steel reinforcing cage was in there to start with. That's taken out to a production floor. It's immediately removed from the mold, and that same mold goes back to the machine to be used again. And the pipes stay on the floor for 10 to sort of 16 hours before they're removed and taken out for further curing and finishing. So as you can see, compared to, call it traditional concrete, it's quite a unique process. So some years ago, and RCPA has been working on this project for well over a decade, we looked at, okay, what's the opportunity? Now, it's come as no surprise to anyone on this call that if you look at a breakdown of the CO2 content in a pipe, that the vast majority is the cement content. So this was based on an example product in Victoria. and you see that sort of more than 80% of the CO2 embodied carbon comes directly from the cement content. So that's obviously the opportunity. So when we went about, originally there was a goal to develop a geopolymer concrete pipe, and there was a lot of work put in the through sort of 2005 through to 2015 on developing a geopolymer. We actually did produce a geopolymer concrete pipe in Victoria. However, it was not easy to make, very sensitive to curing conditions. The chemicals in the that are required to produce it, the activators, had significant OH&S issues from a production perspective. So in 2015, we kind of paused the development of the geopolymer and then sort of went back and said, look, we're not after a zero cement concrete, we're after a low carbon concrete. So we went back and started doing trials. Yeah, as I said, we wanted to avoid OH&S issues. Because of the nature of the process, we need to develop strength quickly. So that is an important factor because we have to, it's a mass-produced product. We need to be able to move the pipes ideally within about 10 hours of casting. So that early strength is critical. And ideally, we wanted to avoid a requirement for significant curing. As you might have noticed on the video I showed, for standard concrete, we don't need to do any curing control. Like the pipes can stand in the ambient conditions. As it turns out, when you do remove Portland cement, you have to provide some level of control around curing, just for predictability as much as anything else. So pretty typical process. In 2015, 2016, we kind of went back to the lab, started working on a range of different options. We got to the point after a couple of years where we found a solution that seemed to work quite well for a dry cast, a vertical cast concrete pipe. That was put into plant trials in 2021, I think it was 2022. Verified that it worked well. There was a need to upgrade equipment, and that's sort of been steadily happening through our factories to support the production of low carbon pipes around the country. And we're now at the stage where we've been in pretty much full scale production in Victoria for about nearly 2 years. Certainly from, actually over 2 years. And we're rolling out the EcoPipe product into our other factories. The next one will be our factory in Queensland, in southeast Queensland, followed by New South Wales, and then our factories in WA at some point in the future. So the results that we get is a carbon sort of profile equivalent to a replacement of 80%, more than 80% of the Portland cement. We do use some activators to basically help that initial nucleation and development of the CSH binding phases. We still have CSH binding phases for the cement chemist in the room. We're not creating anything unusual from a cement concrete perspective. All the admixtures that we use have been tested and comply with the relevant Australian standard. That's just a photo of first production we did in 2021. So what does it get us? This is some information based on, I'll just jump through, an EPD that was done, and LCA models that we did a couple of years ago. So I'm in the process now of updating the LCA and EPD models, partly to incorporate EcoPipe in Victoria, because we've been producing that for over 12 months now, so we can wrap that into an EPD, but also because the product category rules have changed, I think, at least twice, if not possibly 3 times, since we published the first EPD only a couple of years ago. So that's proven to be somewhat of a challenge. But yeah, look, the results speak for themselves. So the fact that we're able to replace more than 80% of the Portland cement with SCMs, that directly leads to a greater than 50% reduction in the embodied carbon for the concrete itself. When it comes to the pipe, the finished pipe, there's a little bit more nuance, because you've obviously got the reinforcing steel that goes into that pipe. That does vary a little bit, but we still end up around the 50% lower embodied carbon in eco-pipe compared to a standard concrete pipe when you account for the reinforcement as well. I thought I'd put those numbers into the format which will be familiar to a lot of people here, is the chart from the embodied guide to carbon that was published. Now, I've put this in the sort of 50 to 65 MPa range. We don't actually have a mandate on compressive strength, but that's where our concretes typically lie, in the sort of the 55 to 60 range. So this just shows here that this is the band that we are in with a standard Portland cement concrete pipe. Quite high. A lot of that's driven by the need to achieve those early strengths. So we do run a relatively high proportion of cement. But with the numbers for eco-pipe, and these will probably change a little bit as we get the new LCA finalised, but we certainly drop down into the sort of the green bands in terms of the MECLA guide. So that was really positive. It's a positive outcome for us as a business. Next. So I'll talk a little bit about some of the mechanical stuff. So obviously we do, well, not obviously, but we do routine concrete compressive cylinder tests, just a photo there. But more importantly, all manufactured concrete pipes undergo what's called proof or ultimate load test, where we take a pipe, we put it under a large load tester, like this, and depending upon the diameter and depending upon the class of pipe you're making, the pipe has to carry a given load without developing a crack more than a certain width, and it has to carry an ultimate load without failure. So this is where we start to depart from, I guess, traditional concrete practice, where at the end of the day, strength of your cylinder doesn't necessarily directly translate to strength of the pipe, because you're testing a structure now. But what it does do is it gives the end owner and asset owner confidence that the structure that they're installing, or that they end up owning, does meet the performance requirements. And we've done many, probably hundreds of tests on eco-pipe concretes to validate that they achieve the strength requirements in the load test. From a durability perspective, concrete pipes are quite unique in that the only durability test is what's called the water absorption test. This is, for those in Victoria, this is very similar to a VPV test. One of the key differences is that the sample is actually taken from a cast pipe. So we cast a pipe. After 2 weeks, we'll then extract cores out of that pipe, and then they're taken to a test laboratory and undergo a drying phase. And then they are boiled for 5 hours at 100 degrees, and you measure the loss and gain of water through that process. So the requirement for the Australian standard is a maximum of 6%. Our typical values for concrete pipe range 4 to 5%. Our experience with eco-pipe has been a fairly significant reduction, and we run in the vicinity of sort of half, so in the sort of 2 to 4% range for water absorption. So that provides a lot of confidence when it comes to the durability. Sorry, my screen is just gone a bit strange, but it's okay. I hope everyone can still see the screen okay. So for additional testing, sorry, I'll have to navigate the mouse. There we go. We've done a range of additional testing to largely satisfy asset owners that there's nothing weird going on or fundamentally unusual about the eco-pipe concrete. So these are just some of the parameters, and these are listed in a technical manual that's on our website. But all of these values, depending upon the location, obviously drying shrinkage is pretty universal. VPV testing is more relevant for those in Victoria. ASR mitigation is quite important. Now, we've done assessments of with mortar testing that shows that the eco-pipe binder mitigates actually better than a 25% ash blend, which is what's traditionally used. Chloride migration, our highest value was at 2.78 by 10 to the minus 12, so that's well under the, for those in New South Wales, well under the requirements. So we've just been able to sort of tick all of the boxes. One other thing that we've done is looked at testing around corrosion resistance. Now this was done because of the concerns that are regularly raised with high SCM concretes around the ability to withstand carbonation related corrosion. So we came up, there's a test that was developed in collaboration with the University of Melbourne, where a cylinder is cast with an embedded reinforcement bar. So you can sort of see there that bar is placed in down the center of the cylinder. The cylinders are then placed in a sodium chloride solution subject to a current and basically monitored. They're monitored until they fail. And what we found in the initial testing was that the OPC cylinders were failing consistently before the eco cylinders. We've done a number of these trials so far. We did one where we carbonated cylinders and showed we got the same sort of result. We didn't see a significant, there was definitely a difference in carbonation. So, you know, the eco pipe cylinders did carbonate to a higher level, but what that didn't translate to is any change in the resistance to corrosion of the steel, even under this condition. So it's not something which is, it's not a standard test method, but it's something that we've done to give confidence that there's no concern. Well, there shouldn't be a concern there. So yeah, just in conclusion, you know, rather than seek a particular goal, we just, you know, we're able to take that outcomes-based approach around low carbon concrete mix designs, and that's largely a function of the ability with concrete pipes to assess the finished structure. You know, we have achieved and do achieve a high strength and durable concrete, meet all of the relevant Australian standards performance requirements, and we can demonstrate that we get equivalent or better performance than we get with a standard Portland cement-based concrete. And just, I've got two more slides. So I probably should wind back a little bit. We have hit a few snags with acceptance by asset owners. A lot of our pipes end up in either council or road authority assets, and there's been a bit of reluctance to, even in light of all the test data that we've been able to provide, to accept this. So some of our more significant projects with EcoPipe have been on private developments, and this is an example of the Melbourne Airport precinct. Last year, we supplied a range of large diameter 1.8 metre pipes to a project that was being constructed on the Melbourne Airport precinct. They were very happy to utilise EcoPipe. You know, we provided all of the conformance and testing data to support that decision. And with this one project, you know, we were able to achieve a reduction of 80 tonnes of CO2. Now, I just like this photo. This is my last slide. I like this photo on the right-hand side, which sort of shows that, unfortunately, for a pipe manufacturer, our products kind of disappear forever. We manufacture them in our factory yard, we deliver them to site, a contractor installs them, and then all things going well, we never see them again. You know, these things should not come up in my lifetime. They should be here for well over a century. So we're sort of like the unseen infrastructure that is on a lot of these construction sites, particularly in the civil industry. But you know, we've been working hard to do this, get this product to work, and you know, we're in regular conversations with road authorities around the country, and we're hoping to be able to get TMR in Queensland to sign off on EcoPipe in the next few months, and then we'll be sort of having some more conversations with Transport for New South Wales and DOT in Victoria to do the same. So that's it from me. Happy if there's anybody got any questions. Like I said, there's more information on the RCPA website around EcoPipe, including some technical data. But yeah, I appreciate the opportunity to present our product and our experience with developing this in the civil precast market.
Thank you so much, Adrian, for the very nice presentations.